Imagine staring into the void of space, not as it is today filled with glittering stars and swirling galaxies, but as it was in the very beginning, a time so ancient, so utterly unfathomable, that light itself had barely begun to exist. This is the cosmic dawn, the universe's first fragile glow, a moment shrouded in mystery and buried under billions of years. What sparked that initial flicker of light? What did the infant universe look like before stars ignited, before galaxies took shape? These questions haunt astronomers and dreamers alike, pulling us into one of science's greatest detective stories. For decades, we've pieced together clues from the faintest whispers of radiation, the echoes of that primordial light. Yet the deeper we look, the more questions arise. Some theories suggest violent collisions of exotic particles. Others paint a picture of slow, delicate awakenings. A few even propose that the first light wasn't light at all, but something stranger, something we've yet to fully understand. This isn't just about astronomy, it's about unraveling the very origin of everything we see, touch, and are. The cosmic dawn isn't just a chapter in a textbook, it's the opening line of the universe's autobiography, written in a language we're still learning to decipher. And that's where things get truly wild. Today, we're diving into 30 of the most mind-bending theories about the universe's first light. From the plausible to the borderline unbelievable, these ideas stretch the limits of our imagination. Could dark matter have played a role? Did black holes flicker to life before stars even had a chance? Each theory is a piece of the puzzle, a flicker of insight into that primordial darkness. So buckle up, because we're about to journey back further than you've ever gone before, to a time when the universe was taking its very first breath. And trust me, what we find there will change how you see the night sky forever. The universe's first light didn't come from stars or galaxies, it came from the aftermath of creation itself. Picture this, a searing, dense fog of particles, so hot and packed together that light couldn't even escape. For nearly 400,000 years after the Big Bang, the cosmos was a swirling, opaque soup of plasma where photons, those tiny packets of light, were constantly bouncing off free electrons trapped in a chaotic dance. Then, in a cosmic instant, everything changed. As the universe expanded and cooled, electrons and protons finally combined to form the first hydrogen atoms. And just like that, the fog lifted. Light broke free, streaming across the newborn universe in every direction. This is the cosmic microwave background, or CMB, the oldest light we can see, a snapshot of the universe at just 380,000 years old. But how do we know this? In 1965, two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon something extraordinary. While tuning their antenna at Bell Labs, they kept picking up a persistent hiss, a faint, uniform signal coming from every corner of the sky. At first, they thought it was interference, maybe even pigeon droppings on their equipment. But after months of testing, they realized they'd found something profound, the echo of the Big Bang itself. This discovery earned them a Nobel Prize and gave us the universe's baby picture, a glow that's been stretched by expansion over billions of years from visible light to microwave wavelength. What makes the CMB so special? It's not just a relic, it's a time capsule. Those tiny fluctuations in temperature variations as small as 1 part in 100,000 reveal the seeds of all cosmic structure. The slightly denser patches became the galaxies and galaxy clusters we see today, while the emptier regions stretched into vast cosmic voids. It's like finding the faint fingerprints of the universe's infancy, still visible in the sky if you know where to look. And here's the wild part, this light is everywhere. Hold up an old analog TV tuned to static, and about 1% of that snow is actually the CMB, the universe's first whisper reaching us across nearly 14 billion years. Yet for all its importance, the CMB is just the beginning of the story. It marks the moment light could finally travel freely, but what came before? What cosmic dramas unfolded in those first 380,000 years of utter darkness? That's where the theories get even more fascinating. Here's a theory that flips everything we thought we knew about the cosmic dawn on its head. What if the first light didn't come from stars or galaxies, but from the death throes of tiny black holes? Picture the early universe, a seething cauldron of energy where conditions were so extreme that black holes could form not from collapsing stars, since stars didn't exist yet, but from the sheer density of matter itself. These wouldn't be the monstrous black holes we think of today, but microscopic ones, some no heavier than a mountain crammed into a space smaller than an atom. And according to Stephen Hawking's groundbreaking work, these tiny black holes wouldn't last forever. They'd slowly leak energy, a phenomenon we now call Hawking radiation. Here's how it works. Quantum mechanics tells us that empty space isn't really empty, it's a bubbling soup of virtual particles popping in and out of existence. Normally, these particle pairs annihilate each other almost instantly, but at the edge of a black hole's event horizon, something weird happens. One particle gets swallowed while the other escapes, stealing a tiny bit of the black hole's mass in the process. Over eons, this leakage would cause the black hole to shrink and eventually vanish in a final burst of radiation. For a primordial black hole formed in the universe's first seconds, that final burst could have come much sooner, perhaps early enough to flicker into existence before the first stars ever ignited. The implications are staggering. If enough of these tiny black holes evaporated in the cosmic dark ages, their combined glow might have illuminated the early universe, creating a faint but detectable light. Some researchers even suggest this could explain mysterious anomalies in the cosmic microwave background, puzzling hotspots or odd fluctuations that don't quite fit our standard models. But here's the catch: we've never actually observed Hawking radiation directly. It's a beautiful idea, mathematically sound, but still waiting for experimental confirmation. And primordial black holes, they're even more elusive. Despite decades of searching, from gravitational wave detectors to gamma-ray telescopes, we've found no definitive proof they ever existed. So why does this theory persist? Because it solves problems other theories can't. If primordial black holes were numerous enough, they could account for some of the universe's missing dark matter. Their evaporations might have seeded the first structures, creating denser regions where galaxies later formed. And let's be honest, there's something thrilling about the idea that the universe's first light didn't come from something as familiar as a star, but from the explosive end of a quantum-scale cosmic predator. It's a reminder that the early universe was a far stranger place than we can imagine, a laboratory for physics so extreme it defies our earthly intuition. Until we find concrete evidence, though, this remains one of cosmology's most tantalizing might-have-beens, a ghostly flicker in the dark, waiting to be proven real. Now let's venture into one of the most elusive possibilities. What if the universe's first light wasn't produced by ordinary matter at all, but by the mysterious collisions of dark matter? Imagine an invisible sea of particles, far outweighing everything we can see, silently shaping the cosmos since its earliest moments. We still don't know exactly what dark matter is, but some theories suggest that when these ghostly particles smash together, they could annihilate in bursts of energy, releasing photons, perhaps even enough to cast a faint glow across the primordial darkness. This isn't as far-fetched as it sounds. Certain dark matter candidates, like WIMP, weakly interacting massive particles, could theoretically collide and self-destruct, converting their mass into gamma rays or other forms of radiation. If this happened in large enough numbers during the cosmic dark ages, it might have lit up pockets of the universe long before the first stars flickered to life. Picture it, an eerie, diffuse light emanating not from blazing suns, but from the annihilation of something entirely unseen. But here's the catch: detecting this dark light is a monumental challenge. Unlike the cosmic microwave background, which blankets the sky in microwaves, any photons from dark matter annihilation would be incredibly faint by now, masked by the glare of stars and galaxies that came later. Even if we trained our most sensitive telescopes on the darkest voids of space, where this signal might linger, we'd still struggle to distinguish it from other cosmic noise. Some scientists are hunting for subtle anomalies in gamma-ray maps or distortions in the cosmic infrared background, hoping to find traces of this ancient, invisible fire. The biggest hurdle: we still don't know dark matter's true nature. Without knowing exactly how these particles behave, we can't predict how often they'd annihilate, or if they even can. Some models suggest the process would have been too rare to matter, while others propose it could have been a dominant light source in specific regions, sculpting the early universe in ways we're only beginning to explore. It's a theory full of tantalizing potential, but until we uncover more about dark matter itself, this faint glow remains just beyond our grasp, a ghostly whisper from the shadows of cosmic history. Before the galaxies we know today, before even the first planets could form, the universe blazed to life with stars unlike anything that exists now, monstrous, searing giants known as population 3 stars. These weren't just the first stars, they were cosmic titans, hundreds of times more massive than our sun, burning so ferociously that their lifetimes were over in mere millions of years. And they were pure, no traces of carbon, oxygen, or iron, just hydrogen and helium, the raw ingredients forged in the Big Bang itself. Here's why they mattered. When these behemoths ignited, their ultraviolet radiation didn't just light up their surroundings, it ripped through the fabric of the early universe. Picture an entire cosmos bathed in the glow of these colossal furnaces, their energy so intense that it shattered the delicate hydrogen atoms drifting between them. Electrons were torn from their nuclei in a process called reionization, ending the so-called Dark Ages, that murky epoch when the universe was still cloaked in neutral gas. This was the moment the cosmos transitioned from opaque to transparent, from darkness to light, setting the stage for everything that followed. But how do we know these stars existed if they died so quickly? Their fingerprints are everywhere. When population 3 stars met their explosive ends, they scattered heavier elements across space, seeding the universe with the building blocks for future stars, planets, and even life. Some astronomers also hunt for their ghostly signatures in the light of the most distant quasars, where the shadows of primordial hydrogen reveal the shadows of these long-dead giants. Others search for distant supernovas so powerful they could only come from stars hundreds of times the mass of our sun. The catch: we've never directly observed one. These stars lived fast, died young, and vanished into the depths of cosmic time. But their legacy is written in the chemistry of the universe itself, in the way galaxies formed, in the distribution of elements, even in the very structure of the cosmic web. They were the universe's first true light-bearers, and without their violent brilliance, the cosmos as we know it might still be lost in darkness. What's truly mind-bending is how different they must have been from modern stars. No planets circled them, no asteroids or comets could yet exist. Their skies, if they had any observers, would have been utterly black, devoid of the glittering constellations we know today. Yet in their short, spectacular lives, they transformed the universe forever. And somewhere out there, in the faintest whispers of ancient light, their story is still waiting to be told. Among the most dazzling and violent objects in the early universe were quasars, supermassive black holes feeding on gas with such ferocity that they outshone entire galaxies. Imagine a cosmic hurricane where matter spirals into oblivion at nearly the speed of light, heating up to millions of degrees and blasting out enough energy to be seen across billions of light years. These weren't just bright, they were the ultimate lighthouses in the cosmic dark, and some of them may have flickered on before the first stars even had a chance to shine. What made quasars so special? Unlike the slow burn of stars, quasars were powered by gravity itself. The raw, unfiltered energy of black holes devouring entire suns worth of material every year. As gas and dust swirled into these gravitational pits, friction turned the infalling matter into a white-hot disk, spewing out torrents of ultraviolet and X-ray radiation. This wasn't gentle starlight, it was a tsunami of energy powerful enough to tear electrons from hydrogen atoms in a process called reionization. The universe, once cloaked in neutral gas, became transparent again, all thanks to the relentless glare of these ravenous monsters. But here's the twist: quasars didn't just light up the cosmos, they shaped it. Their radiation acted like cosmic blowtorches, carving out vast bubbles of ionized gas around them. Some theories suggest these bubbles might have accelerated the formation of the first galaxies, compressing gas at their edges and triggering star formation. Others argue quasars could have stunted growth in nearby regions, their radiation so intense it blew away the raw material needed to build stars. Either way, their influence was profound, etching their mark into the fabric of the early universe. The hunt for the earliest quasars is one of astronomy's greatest challenges. The current record holder, J0313-1806, blazed into existence just 690 million years after the Big Bang, a time when the universe was barely 5% of its current age. Finding these ancient beacons isn't just about breaking records, it's about piecing together how black holes grew so massive so quickly. Did they start as colossal seeds from the collapse of primordial gas clouds? Or did they build up gradually, merging and feeding in a frenzy of cosmic competition? Each discovery peels back another layer of the mystery. Yet for all their brilliance, quasars couldn't have been the universe's only light source. They were rare, scattered like jewels across the vastness of space, while the glow of reionization was everywhere. That's why most scientists think quasars teamed up with the first stars and galaxies to lift the cosmic veil. Together, they flooded the universe with photons, ending the darkness and setting the stage for everything that followed. What's haunting is how fleeting their era was. As the universe expanded and gas supplies dwindled, quasars faded into obscurity, their fuel exhausted. Today, their descendants, supermassive black holes like the one at the heart of our Milky Way, are quiet shadows of their former selves. But for a brief, glorious moment, they ruled the cosmos, their light piercing the darkness and helping to build the universe we call home. And somewhere out there, their earliest rays are still traveling, carrying secrets from the dawn of time. What if the universe's first light wasn't just a consequence of the Big Bang, but carried echoes of an even more explosive event that came moments before? Enter cosmic inflation, the theory that the infant universe underwent a growth spurt so extreme it expanded faster than the speed of light, doubling in size at least 60 times in a fraction of a second. This wasn't just rapid expansion, it was a reshaping of reality itself, and hidden in the faint polarization patterns of the cosmic microwave background, some scientists believe we might find the scars of that violent birth, a primordial light show that predates even the CMB. Here's how it could work. During inflation, the universe wasn't just stretching, it was a seething quantum foam where tiny fluctuations in energy flickered in and out of existence. Most of these fluctuations smoothed out as space expanded, but a few got stretched to cosmic proportions, frozen into the fabric of spacetime. These became the seeds for everything: galaxies, clusters, the vast cosmic web. But some theories suggest these quantum ripples might have also produced something far more fleeting: bursts of primordial light, sparked by the violent stretching of space itself. Imagine the universe ringing like a bell after a colossal strike, emitting gravitational waves so powerful they could have disturbed the electromagnetic field, creating photons in their wake. The evidence: it might be written in the CMB's polarization, the way its light waves align as they travel through space. Certain swirling patterns, called B modes, could be the fingerprint of inflation's gravitational waves. If we find them, it wouldn't just confirm inflation, it would open a window into the universe's first trillionth of a second, a realm where physics as we know it breaks down. The challenge: these signals are absurdly faint, buried under cosmic noise and dust. Projects like the BICEP and Planck telescopes have scoured the skies for clues, but so far the smoking gun remains elusive. What makes this theory so thrilling is its audacity. It suggests that the universe's first light wasn't just a passive afterglow, it was an active message encoded in the chaos of creation. And if we're right, those photons might still be whispering to us, carrying secrets from a time before time. The catch: we're hunting for ghosts. The energy scales involved are so far beyond anything we can recreate that even our best detectors might miss the signal. Yet the pursuit continues, because if we crack this code, we'll have done more than solve a cosmic mystery. We'll have touched the moment when reality itself flickered into being. Among the most ghostly particles in the universe, neutrinos barely interact with matter. Trillions pass through your body every second without a trace. But what if these elusive particles, left over from the Big Bang's chaotic aftermath, secretly shaped the cosmos by transforming into light? This theory hinges on a radical idea: that in the early universe's extreme heat and density, neutrinos might have decayed into photons, flickering into existence long before stars could ignite. Neutrinos are cosmic enigmas. They're nearly massless, chargeless, and famously indifferent to ordinary matter. According to the Standard Model, our best blueprint for particle physics, they shouldn't decay at all. But here's the twist: if neutrinos have even a tiny bit of mass, and we now know they do, and if undiscovered quantum quirks exist beyond the Standard Model, these particles could theoretically break down over eons into lighter particles, including photons. In the young universe, where energies were unimaginably high, this decay might have happened explosively fast, flooding space with bursts of primordial light. Why does this matter? The cosmic microwave background shows a universe bathed in near-uniform light, but tiny irregularities in that glow hint at deeper mysteries. If neutrino decay photons contributed to reionization, the process that lifted the universe from darkness, they could explain anomalies in the CMB's polarization patterns. Some models even suggest these decays might have left imprints in the large-scale structure of the cosmos, subtly altering how galaxies clustered together. The catch: no one's ever observed a neutrino decaying. The Standard Model insists stable neutrinos are dark, meaning they don't emit light. To make this theory work, we'd need new physics, perhaps extra dimensions, undiscovered particles, or a subtle rewriting of quantum rules. Experiments like IceCube and future neutrino observatories could hunt for hints, but for now, this idea lies in the realm of tantalizing what-ifs. What's fascinating is the scale of the proposal. Neutrinos outnumber atoms by billions to one, so even a tiny fraction decaying could have lit up the cosmos. Picture it: a universe dark and silent, suddenly shimmering with the collective glow of countless vanishing neutrinos. A light born not from fire or collisions, but from the quiet death of the universe's most aloof particles. Until we crack neutrino physics further, this remains one of cosmology's most elegant maybes, a whisper from the shadows of particle physics. Imagine a particle so elusive it could be the key to two cosmic mysteries at once: dark matter and the universe's first light. That's the tantalizing promise of actions, hypothetical particles born from quantum theory's most elegant solutions. Unlike the violent explosions of stars or the crushing gravity of black holes, actions could have created light through a quiet, almost poetic process, transforming invisible energy into visible photons as they danced through magnetic fields in the early universe. The story starts with a problem in particle physics. In the 1970s, scientists realized the Standard Model had a glaring hole. It couldn't explain why subatomic particles called neutrons don't wobble as much as they should in electric fields. To fix this, theorists proposed actions, feather light particles acting as cosmic referees, keeping quantum interactions in perfect balance. But here's where it gets cosmic. If actions exist, they wouldn't just solve a tiny physics puzzle. They might make up most of the universe's dark matter, silently suffusing space since the Big Bang. And under the right conditions, these ghostly particles could flicker into something we can actually see. Here's how it works. In the presence of strong magnetic fields, like those around newborn galaxies or threading through the primordial cosmos, actions could undergo a metamorphosis. Their quantum fields might oscillate, shedding energy in the form of photons. This isn't science fiction. It's a phenomenon predicted by quantum electrodynamics called the Primarkov effect. Picture an axion drifting through a nest of magnetic field lines, suddenly splitting into two particles, one of them a photon, a spark of light where there was none before. Over eons, countless actions undergoing this conversion could have bathed patches of the early universe in a faint, eerie glow. The implications are staggering. If axion-to-photon conversion happened on cosmic scales, it might explain puzzling gaps in our maps of the cosmic microwave background, regions where the light seems just a bit too bright or too dim. Some researchers even speculate that axion decay could have jump-started reionization, helping to lift the universe from darkness before stars took over. But the real beauty of this theory, we might not need telescopes to test it. Down here on Earth, experiments like ADMX, the Axion Dark Matter Experiment, are hunting for actions by recreating their predicted light show in reverse. Inside powerful magnetic fields, scientists wait for phantom photons to materialize as actions, their detectors tuned to the faintest possible signals. It's like trying to hear a whisper in a hurricane, but if they succeed, it would confirm not just a new particle, but a hidden chapter in cosmic history. What makes actions so compelling is their dual role. They could be the missing piece of dark matter, the solution to a quantum conundrum, and the architects of the universe's first light, all wrapped into one. Yet for now, they remain shadowy figures at the edge of physics, their existence hanging on the slimmest of possibilities. Every flicker in a detector, every anomaly in the CMB, brings us closer to knowing whether these ghostly particles lit up the cosmos, or if we're chasing the most beautiful mirage in modern science. One thing's certain, if actions are real, they rewrite not just particle physics, but the story of light itself. Long before galaxies took shape, the universe was a boiling ocean of plasma, so dense that sound waves could ripple through it like thunder through a storm. These weren't ordinary sound waves, they were baryon acoustic oscillations, pressure pulses traveling at half the speed of light, compressing matter into vast spherical shells that would shape the cosmos for billions of years. And here's the wild part. When the cosmic microwave background froze into existence, it captured these oscillations like a fingerprint, revealing where pockets of light and matter were destined to clump together. Picture the early universe as a colossal bell struck by the Big Bang. Matter and radiation were locked in a tug-of-war gravity pulling particles inward, while the intense pressure of photons pushed them apart. This created rhythmic waves, crests where matter piled up and troughs where it thinned out. Over hundreds of thousands of years, these waves spread outward, carving bubbles in the plasma. Then, in a flash, the universe cooled enough for atoms to form, releasing the CMB and freezing those waves in place. What we see today are the remnants of those ancient echoes, slightly hotter spots where matter was compressed, cooler spots where it was rarefied. But these oscillations did more than just leave marks on the CMB. They set the stage for everything that followed. The denser regions became the nurseries for galaxies, with clusters forming at the peaks of those primordial ripples. Astronomers can actually measure this. The average distance between galaxies today, about 500 million light-years, matches the scale of those original sound waves. It's as if the universe handed us a ruler etched into the fabric of space itself. What's truly mind-bending is how these oscillations might have sparked localized light bursts. In regions where matter piled up most densely, the first stars could have ignited earlier, bathing their surroundings in ultraviolet radiation. Meanwhile, the troughs stretched thin and empty remained dark longer. This cosmic patchwork of light and shadow didn't just influence galaxy formation. It sculpted the universe's large-scale structure, leaving behind a web of voids and filaments we still trace today. The evidence looked no further than galaxy surveys like the Sloan Digital Sky Survey, which maps millions of galaxies in intricate 3D. Their distribution isn't random. It follows a predictable rhythm, a whisper of those ancient sound waves. Even more striking, the CMB's temperature fluctuations line up with these patterns, confirming that the seeds of today's cosmic structures were planted in the universe's first moments. Why does this matter? Because baryon acoustic oscillations are more than a fossil, they're a tool. By measuring their scale, astronomers can track how the universe has expanded over time, probing the nature of dark energy and the curvature of space itself. Those primordial ripples didn't just shape the past, they're helping us decode the future of the cosmos. And somewhere, hidden in the faintest echoes of that early plasma, lies the story of how light first found its way through the darkness. Cosmic strings might sound like something straight out of science fiction, but these bizarre one-dimensional defects in space-time could have played a starring role in the universe's first light show. Picture the early cosmos not just as a smooth expanse, but as a fractured landscape where ultra-thin filaments of pure energy, thinner than a proton but stretching across light years, vibrated like guitar strings plucked by the Big Bang itself. According to string theory, these cosmic strings wouldn't just sit quietly. They'd whip through space at near light speed, kinking and twisting until they released bursts of gravitational waves, and possibly, just possibly, light. How could something so strange exist? The math points to phase transitions in the newborn universe. Think of it like water freezing into ice. As the cosmos cooled from the Big Bang's unimaginable heat, symmetry-breaking events might have left behind topological scars in spacetime. These scars would manifest as cosmic strings, unimaginably dense and under such immense tension that a single kilometer-long string could outweigh Earth. But here's the twist. When these strings vibrate, they don't just create gravitational ripples, they could also produce electromagnetic radiation through a process called cusp emission. At the sharpest kinks in a string's spiral, particles might get accelerated to extreme energies, colliding to spark fleeting bursts of photons, the catch. We've never detected a cosmic string. Unlike black holes or neutron stars, they leave no shadow or accretion disk. Their most promising signatures, double images of distant galaxies warped by string gravity, or abrupt jumps in the cosmic microwave background, remain elusive. Yet the hunt continues because the payoff would rewrite physics. Finding even one string would validate aspects of string theory, shine a light on unification energy scales we can't recreate in particle colliders, and potentially explain anomalies in the CMB's polarization patterns. Some models even suggest networks of decaying strings could have seeded early reionization, their death throes flooding the cosmos with UV light before stars took over. What makes this theory so compelling is its audacity. It dares to suggest that the universe's first glow wasn't from stars or particles, but from spacetime itself unraveling. And if strings exist, their faint vibrations might still resonate through the cosmos today, a ghostly hum from the dawn of time, waiting for the right detector to listen. Until then, they remain one of cosmology's most enchanting what-ifs, a reminder that the early universe was stranger than we can imagine. In the searing heat of the early universe, light didn't just travel, it fought for survival. Photons, those seemingly weightless particles of light, weren't just passive bystanders. They were locked in a violent dance with each other, smashing together with enough energy to birth entirely new particles. This wasn't just illumination, it was alchemy, where pure energy transformed into matter and back again in a frenzied loop. And somewhere in that chaos, the universe's first true light might have been born not from stars or plasma, but from the sheer force of photons colliding at unimaginable speeds. Here's how it works. Today, light mostly passes through other light. Your flashlight beam doesn't scatter when it crosses a streetlight. but rewind to the universe's first seconds when temperatures soared above 1 trillion degrees and photons weren't just waves, they were bullets. Packed together in that dense primordial soup, their collisions became so energetic they could spontaneously create particle-antiparticle pairs, electrons and positrons, quarks and antiquarks, in flashes of quantum spontaneity. Most of these pairs would almost immediately annihilate each other, releasing fresh photons in the process. It's like a cosmic game of bumper cars where every crash spawns new riders, each collision potentially birthing the next flicker of light. What makes this idea so fascinating is the scale of destruction and creation. In those first moments, the universe was so hot that photons weren't just visible light. They were gamma rays packing enough punch to warp spacetime itself. When two of these ultra-high-energy photons collided, they could briefly form a virtual electron-positron pair thanks to quantum uncertainty. Normally, these pairs vanish instantly. But in the early universe's extreme environment, some might have lasted just long enough to get caught in the gravitational tides of spacetime fluctuations, stretching apart before annihilation. The result, a burst of slightly lower energy photons, the first sparks in an otherwise opaque cosmos. The echoes of this process might still be visible today. Some theories suggest these photon-photon battles could have left faint imprints on the cosmic microwave background, patches where the light is subtly polarized or dimmer than expected. Others propose that the remnants of those early particle showers influenced how matter clumped together, seeding the first structures in the universe. There's even a wild possibility that some of the high-energy gamma rays we detect from distant quasars aren't just cosmic accidents. They could be the last survivors of this primordial light-making mechanism, photons that have traveled billions of years unchanged. Yet for all its elegance, this theory faces hurdles. The energies required are so extreme they dwarf anything we can recreate in particle colliders. And without direct observations of those first collisions, much of the evidence remains circumstantial, a puzzle where key pieces are missing. But that's what makes cosmology thrilling. Every flicker of ancient light carries clues, and somewhere in the chaos of those early photon duels, the universe might have lit its own way forward, not with fire or fusion, but with the raw, transformative power of pure energy. Deep in the equations of particle physics lies an elegant idea. What if every known particle has a hidden twin? This is supersymmetry, or SUSY for short, a theory that could solve some of the universe's biggest mysteries while rewriting the story of its first light. According to SUSY, particles like electrons and quarks would have heavier, undiscovered counterparts, electrons, squarks, and perhaps most intriguingly, neutralinos. These hypothetical particles aren't just extras in the cosmic cast. They could be the key to dark matter and the architects of the universe's earliest glow. Neutralinos are particularly fascinating. If they exist, they'd be a mix of supersymmetric particles, stable enough to survive from the Big Bang until today, making them prime dark matter candidates. But here's where light comes in. In the dense, high-energy environment of the early universe, neutralinos might not have stayed silent. Some models suggest they could have collided and annihilated, transforming their mass into bursts of energy, including photons. This wouldn't be a gentle glow, but a cascade of high-energy radiation, potentially lighting up pockets of the cosmos before stars took the stage. The process hinges on SUSY predictions. When two neutralinos meet, they could destroy each other in a flash, producing quark-antiquark pairs or even Higgs bosons. These would then decay further, eventually yielding gamma rays, the universe's most energetic form of light. Over time, as the universe expanded, those gamma rays would redshift into less extreme wavelengths, possibly contributing to the diffuse background light we still see today. But there's a glaring problem. We've never found proof that supersymmetric particles exist. The Large Hadron Collider, the most powerful particle smasher ever built, has hunted for SUSY for over a decade. So far, no squarks, no selectrons, no neutralinos. Every time the LHC increases its energy or refines its detectors, physicists hold their breath only to be met with more ordinary particles and empty corridors in the data. Some argue SUSY might simply be hiding its particles just beyond our current energy reach. Others whisper that nature might not play by supersymmetric rules after all. Yet SUSY isn't down for the count. Even without direct detection, its fingerprints might linger in other ways. If neutralino decay helped reionize the early universe, subtle irregularities in the cosmic microwave background could hold clues. Alternative experiments, like those searching for dark matter's faint signals in underground labs, might still stumble upon a neutralino's signature. And let's not forget, supersymmetry isn't just about particles. It's a framework that elegantly ties together gravity, quantum mechanics, and the fundamental forces. Many theorists cling to it not for lack of imagination, but because it's too mathematically beautiful to abandon outright. So where does that leave us? SUSY remains a brilliant what-if, a theory that could explain dark matter, cosmic light, and the universe's deepest symmetries, all while hovering just out of reach. Whether it's a ghost in the machine or a reality waiting to be uncovered, one thing's certain: if neutralinos ever flickered into existence, their light would be more than just illumination. It would be a message from the hidden layers of reality itself, at scales so tiny they defy comprehension, trillions of times smaller than an atom. The very fabric of space-time might not be smooth at all, but a seething, chaotic froth known as quantum foam. Picture an ocean during a hurricane with waves crashing in every direction, except here, the waves are space-time itself, bubbling with fluctuations so violent that temporary particles flicker in and out of existence. And in this frenzy, some scientists speculate that something extraordinary could have happened: microscopic flashes of light bursting forth from the foam itself, illuminating the universe in its first moments. This isn't just poetic imagination, it's a consequence of quantum gravity's most radical theories. At the Planck scale, where distances are measured in units of 10 to the minus 35 meters, gravity and quantum mechanics collide in ways we barely understand. Einstein's relativity paints spacetime as a smooth continuum, but quantum mechanics insists everything is discrete and jittery. Quantum foam is the messy compromise, spacetime so warped that infinitesimal black holes and wormholes might pop into existence for fleeting instants before vanishing again. And it's in these ephemeral distortions that light could have been born. Here's how it might work. When a tiny region of spacetime fluctuates violently enough, it could briefly concentrate energy into something resembling a particle, perhaps even a photon. These wouldn't be the orderly waves of light we know today, but erratic sparks, here one moment and gone the next. Some models even suggest that these flashes could have collectively contributed to a faint background glow, a primordial shimmer woven into the fabric of the cosmos before stars or galaxies existed. The challenge: we'll likely never observe quantum foam directly. The Planck scale is so far beyond our current experimental reach that probing it would require particle accelerators the size of the solar system. Even the most sensitive detectors, like gravitational wave observatories, can't pick up fluctuations this minuscule. That's why quantum foam remains in the realm of mathematical elegance rather than hard evidence, a beautiful idea that might forever linger at the edge of testability. Yet its implications are profound. If spacetime is truly foamy at its core, it could mean that light isn't just something that travels through the universe, it's something the universe itself occasionally hiccups into being. And while we may never catch these Planck scale flashes in action, their ghostly traces might still linger in the subtlest patterns of the cosmic microwave background, waiting for a theory bold enough to decode them. Until then, quantum foam remains one of cosmology's most tantalizing mysteries, a reminder that the universe's first light might have been far stranger than we dare to dream. Black holes are often painted as cosmic vacuum cleaners, swallowing everything including light without a trace. But what if, in the early universe, certain black holes actually did the opposite, acting like rogue power plants spewing light into the darkness? This is the bizarre realm of superradiance, a phenomenon where spinning black holes don't just consume energy, they amplify it, extracting power from their own rotation to create bursts of radiation. And in the chaotic infancy of the cosmos, this process might have been one of the first sources of illumination. At the heart of superradiance lies the ergosphere, a warped region just outside a rotating black hole's event horizon where spacetime itself gets dragged around like water caught in a whirlpool. Here, the laws of physics get twisted. Normally, particles or waves that venture too close to a black hole are doomed, but in the ergosphere, something extraordinary can happen. If a wave like light or even gravitational ripples enters this zone with just the right frequency, it can steal a fraction of the black hole's rotational energy, emerging stronger than before. Picture shouting into a tornado and having your voice come back louder, powered by the storm itself. That's superradiance in action. The real magic comes from the Penrose process, named after physicist Roger Penrose, who first realized black holes could be cosmic energy thieves. In this scenario, a particle entering the ergosphere splits in two. One fragment falls into the black hole, while the other escapes with extra energy siphoned from the black hole's spin. Over time, this could slow the black hole's rotation, but in exchange, it floods the surroundings with high-energy radiation. Now imagine this on a cosmic scale: primordial black holes spinning furiously in the early universe, acting like lighthouses as superradiance amplifies ambient light or even generates new photons from the quantum foam. But why would this matter for the first light? In a universe still cloaked in darkness, even a few energetic black holes could have created hotspots of radiation, jump-starting reionization in their vicinity. Some models suggest superradiant instabilities could have produced vast clouds of low-frequency light photons stretched out by expansion, but still numerous enough to nudge the cosmos toward transparency. The echoes of this might linger in today's cosmic background radiation, subtle anomalies that hint at regions where black holes once blazed like beacons. The catch: superradiance requires precise conditions. The black hole must spin fast enough, and the incoming waves need just the right frequency to trigger amplification. Too slow and the effect fizzles, too chaotic and the energy dissipates. Yet in the dense, turbulent early universe where black holes were smaller and spun wildly, the odds tilt in favor of these light show scenarios. It's a reminder that even the darkest objects in the cosmos might have once been secret architects of light, turning the very physics of oblivion into a spark of creation. What's truly humbling is how speculative this remains. We've never directly observed superradiance around black holes, though some researchers comb through gravitational wave data for hints. Until we do, it stands as one of the most elegant what-ifs in cosmology, a testament to the universe's flair for turning destruction into illumination. And if the math holds, those first flickers of light might not have come from stars or plasma, but from the whirlpool edges of spinning black holes, rewriting darkness into dawn. There's a kind of black hole so strange it defies intuition, one forged not from collapsing stars, but from pure light itself. This is the Kugelblitz, a German word meaning ball lightning, and it's exactly as terrifying as it sounds. Imagine concentrating enough photons into a tiny space that their collective energy warps spacetime, creating a singularity out of nothing but radiation. No matter, no debris, just light so intense it bends the universe into a trap from which not even light can escape. Here's where physics gets surreal. According to Einstein's equations, energy and mass are interchangeable. That's what E equals mc squared tells us. So if you cram enough energy, whether from matter or light, into a small enough volume, gravity takes over. For a Kugelblitz, the threshold is absurdly high. You'd need to focus the energy of entire stars into a region smaller than an atom. But in the early universe, conditions might have been extreme enough to pull it off. Picture the cosmic dawn, a time when space crackled with gamma rays and primordial plasma. In the chaos, quantum fluctuations or collapsing regions of false vacuum could have briefly concentrated photons beyond critical density, sparking fleeting blitzes like matches struck in the dark. What happens next is even wilder. These black holes born from light wouldn't last forever. Thanks to Hawking radiation, they'd evaporate slowly at first, then explosively as they shrank. And here's the twist: their death throes could recycle energy back into new photons. It's as if the universe played a cosmic game of catch, turning light into a black hole, only to spit it back out as light again. Some theories suggest this process might have left behind subtle imprints. An excess of high-energy gamma rays in certain directions, or odd distortions in the cosmic microwave background where spacetime itself briefly tied itself into knots. But blitzes aren't just a relic of the past. If we could somehow recreate one in a lab, a feat requiring energies far beyond our current technology, it would revolutionize energy storage, propulsion, even our understanding of quantum gravity. Of course, the risks are as colossal as the rewards. A blitz gone wrong could unleash a black hole capable of devouring the experiment, the lab, and possibly the planet. For now, they remain a tantalizing thought experiment, a reminder that light isn't just something we see, it's a force that can bend the very rules of reality. The real magic lies in the questions left unanswered. Could blitzes have been dark matter candidates, their evaporating remnants lingering as ghostly radiation? Might they explain mysterious flashes in deep space that our telescopes can't quite place? Until we find a way to probe those first moments of cosmic history, these fiery enigmas will keep burning at the edges of our imagination, black holes forged not in darkness, but in the universe's first brilliant blaze. If black holes are cosmic vacuum cleaners, endlessly swallowing matter and light, then white holes are their mirror opposites, cosmic fire hoses, violently spewing out everything that comes near. These hypothetical objects, born from the same equations that predict black holes, have never been observed, but in the chaos of the early universe, they might have been the ultimate fireworks, erupting with enough brilliance to outshine entire galaxies. Picture a white hole as a black hole running in reverse. Where a black hole's gravity is so strong nothing escapes, a white hole's repulsion is so fierce nothing can enter. Matter and energy erupt from its center like water from a geyser, propelled outward by forces we barely understand. According to general relativity, if you could somehow film a black hole's formation and play the tape backward, you'd see a white hole, a burst of light and particles exploding into existence. Some theorists even suggest that every black hole might be connected to a white hole through a wormhole, turning the universe into a vast network of cosmic fountains and drains. But here's where it gets wild. In the early universe, conditions might have been extreme enough for white holes to form naturally. Imagine the aftermath of the Big Bang, where spacetime itself was still settling into shape. Quantum fluctuations or regions of warped geometry could have pinched off into self-contained bubbles, popping open as white holes, each one a sudden eruption of energy in an otherwise dark cosmos. These wouldn't be the quiet, persistent objects we fantasize about today. They'd be fleeting, violent events, vanishing almost as quickly as they appeared. Yet in their brief lives, they could have flooded space with radiation, jump-starting ionization in their surroundings and leaving behind pockets of heated gas where galaxies would later form. The catch: white holes violate the second law of thermodynamics, which says entropy, the universe's tendency toward disorder, always increases. A white hole's orderly eruption of energy seems to defy that. Plus, no known physical process explains how one could form naturally after the Big Bang's initial chaos. That's why most physicists consider them mathematical curiosities rather than real cosmic phenomena. But there's a tantalizing loophole. If white holes did exist, they'd likely be unstable, collapsing almost instantly into black holes or dissipating into radiation. Any light they produced would be a flash in the pan, bright, brief, and nearly impossible to spot across billions of years. Still, the idea persists because it solves puzzles. Some researchers speculate that certain gamma-ray bursts, mysterious explosions of high-energy light, could be the dying gasps of ancient white holes. Others wonder if the universe's inexplicable uniformity, the near-perfect balance of the cosmic microwave background, might hint at a white hole's explosive smoothing effect. And let's not forget the sheer poetry of it, a cosmos where darkness isn't just punctuated by starlight, but by the shockwaves of white holes, their brilliance etching temporary constellations into the void. Until we find proof, though, they remain one of physics' most enchanting mirages, a glimpse of what the universe might have been, if only for a moment. Imagine if the very fabric of reality was built on a lie, a precarious ledge where the universe's energy balance isn't truly stable, only temporarily frozen in place. That's the spine-tingling premise of vacuum decay, a theory suggesting the cosmos might have briefly slipped into a lower energy state in its infancy, unleashing a cataclysmic burst of light. At the heart of this idea lies the Higgs field, that invisible ocean of energy that gives particles their mass. According to quantum field theory, what we call empty space isn't empty at all. It's a simmering quantum soup where fields like the Higgs fluctuate constantly. Most of the time, these fields sit in what's called a false vacuum, a state that seems stable but isn't quite the lowest possible energy configuration. It's like a marble resting in a shallow dent atop a mountain. One nudge and it could roll all the way down. Now picture the early universe, a cauldron of unimaginable energy where quantum fluctuations were violent enough to push the Higgs field over that edge. If a tiny pocket of space decayed to a true vacuum, a lower energy state, it would release an expanding bubble of energy, rewriting the laws of physics within its wake. At the bubble's boundary, particles would gain or lose mass abruptly, and the sudden rearrangement could produce an apocalyptic flash of photons. This wouldn't just be light, it would be a fundamental reset button for reality, propagating outward at nearly the speed of light. Here's where it gets even wilder. Some models suggest that if this happened in the universe's first moments, the energy release might not have been uniform. Instead of a single, all-consuming wave, there could have been countless microscopic decay events, each one a tiny spark in the darkness. These flashes might have collectively contributed to reionization, helping to lift the cosmic fog before stars took over. The echoes of these events could still linger in the cosmic microwave background as peculiar temperature variations, subtle scars from when space-time itself flickered like a guttering candle. But vacuum decay isn't just about the past, it's a high-stakes puzzle for our future. If the Higgs field is indeed in a false vacuum, as some precision measurements hint, then a decay event could theoretically happen again anywhere, anytime. A single quantum fluctuation in some distant galaxy might trigger a new bubble of true vacuum, racing toward us at light speed with no warning. The good news: it's statistically absurdly unlikely. The universe is 13.8 billion years old, and if it hasn't happened yet, it probably won't. But the fact that it's even possible forces us to confront a humbling truth. The laws of physics we take for granted might not be permanent. They could be local, temporary bylaws in a cosmos capable of rewriting its own rules. What makes this theory so fascinating isn't just its apocalyptic potential, it's the way it blurs the line between destruction and creation. A vacuum decay event in the early universe wouldn't just erase, it could transform, sculpting regions of space with new properties we can't even imagine. Perhaps some of the anomalies in our cosmic map's pockets where dark energy behaves oddly or matter clumps unexpectedly are relics of these ancient phase transitions. Until we unlock the full story of the Higgs field, vacuum decay remains one of cosmology's most exhilarating what-ifs, a reminder that the universe's first light might have been more than just illumination. It could have been the universe reinventing itself on the fly. What if the universe's first light wasn't generated from within our three-dimensional cosmos at all, but from the distant two-dimensional edges of reality itself? This is the radical promise of the holographic principle, a theory suggesting that all the information in our universe, every star, every atom, even the photons streaming through space, might actually be encoded on a vast cosmic boundary, like a projection flickering into existence from the walls of a black hole. And if that's true, the earliest light we see could be little more than a shadow of deeper interactions playing out on the fringe of space-time. The math behind this idea comes from string theory, specifically something called the add-s/CFT correspondence, a concept so profound it's been called a theory of everything in waiting. Here's the gist. In certain hypothetical universes with negative curvature, imagine a cosmic saddle shape. The physics inside the bulk of that space can be perfectly mirrored by quantum theories operating on its lower dimensional boundary. It's like watching a movie and realizing the entire story is being dictated by patterns etched onto the film's edge, except in this case, the movie is reality itself. Now apply this to the early universe. If the holographic principle holds, then the seething quantum chaos of the Big Bang might have first played out on a primordial 2D surface, with our familiar 3D cosmos emerging as a kind of illusion. And just as heat radiates from a hot plate, those frenzied boundary interactions could have emitted energy photons into the newborn universe. This wouldn't be light as we know it, born from stars or particles, but a byproduct of information processing on the cosmic hard drive. The implications are staggering. It could mean that the cosmic microwave background's intricate patterns aren't just random fluctuations, they're a translation of quantum data from the universe's outer shell. Some researchers even speculate that anomalies in the CMB, like unexpected cold spots or unusual polarization, could be glitches in this cosmic projection, hints that the hologram isn't perfect. Imagine finding a pixel out of place in reality itself. But here's the catch: we don't live in an anti-de Sitter space, the negatively curved universe where add-s/CFT works most cleanly. Our cosmos is flat or nearly so, and no one's yet figured out how to rigorously extend the holographic principle to our actual universe, yet the tantalizing parallels remain. Black holes, for instance, seem to obey holographic rules. Their entropy scales with surface area, not volume, as if their insides are painted onto their event horizons. If the whole universe operates this way, then those first flickers of light might not just illuminate the past, they could be clues to the true, low-resolution nature of reality. What's mesmerizing is how this flips the script on cosmic dawn. Instead of searching for the first stars or particles, we might need to look deeper, to ask whether light itself is just a side effect of something far stranger, a code written on the edges of existence. Until we crack the holographic puzzle, though, it remains one of physics' most beautiful maybes, a reminder that the universe's oldest light could be less about what we see and more about where we're seeing it from. What if the Big Bang wasn't the beginning, just the middle? Loop quantum gravity, a radical alternative to string theory, paints a picture where the universe cycles through endless collapses and rebirths, a cosmic heartbeat where each bang follows a crunch. In this model, our universe might be just the latest in an infinite series, and the first light we detect could carry echoes of a cosmos that existed long before our own. At the heart of this idea is spacetime's atomic structure. Unlike classical physics, where space is smooth and infinitely divisible, loop quantum gravity suggests it's woven from tiny, indivisible threads. Think of it as a fabric where even the stitches have stitches. When gravity gets extreme, like at the center of a black hole or the moment of the Big Bang, these threads resist further compression. Instead of collapsing into a singularity of infinite density, the universe hits a quantum wall and bounces back. It's as if the cosmos took a deep breath, held it at the smallest possible scale, then exploded outward again in a new Big Bang. Now, here's where light enters the story. During the crunch phase, the collapse of the previous universe, matter and energy wouldn't just vanish. They'd be compressed to unimaginable densities, heating up until the entire cosmos glowed like the inside of a star. As the bounce occurred, that trapped radiation would flood outward, mixing with the newborn universe's energy. Some theorists speculate this could explain oddities in the cosmic microwave background, like unexpected temperature variations or swirls in polarization that don't fit standard Big Bang predictions. These anomalies might be cosmic bruises, scars from a universe that came before, but proving any of this is a nightmare. The bounce would have erased most traces of the prior universe, like a chalkboard wiped clean before a new equation is written. Any light surviving the transition would have been stretched and diluted by expansion, its signals buried under eons of cosmic noise. Even if we spotted a strange pattern in the CMB, how could we distinguish it from random fluctuations or unknown physics in our own universe's infancy? Current telescopes lack the precision to test these subtle predictions, though next-generation observatories like the planned Light-Bird satellite aim to scour the CMB for clues. The real magic of this theory lies in its audacity. It doesn't just tweak the Big Bang, it redefines it, turning a singular event into a phase in an endless cycle. And if it's right, the universe's first light wasn't just a beginning, it was a rebirth, a photon's journey across the void between cosmic lifetimes. Until we find harder evidence, though, the Big Bounce remains a dazzling hypothesis, a reminder that the past might be stranger than we ever dreamed. Imagine living in a universe with more dimensions than we can see, where light doesn't just travel through space and time but slips between hidden layers of reality. This isn't science fiction, it's string theory's bold proposition, and it might explain how the first photons illuminated our cosmos. According to this idea, our familiar three-dimensional universe could be floating like a thin sheet, a brain, in a higher dimensional space, with extra dimensions curled up so tightly we'll never perceive them directly. But in the extreme energies of the early universe, those hidden dimensions might have flexed, warped, or even torn, allowing energy to spill into our world as light. Brain-world cosmologies take this even further. Picture two parallel brains vibrating in a higher dimensional bulk, occasionally colliding with cataclysmic force. These collisions could have released enough energy to trigger Big Bang-like conditions, not just once but repeatedly. In some models, photons from these collisions wouldn't just originate on our brain, they might cascade in from others, like echoes of cosmic fireworks happening just out of view. The light we perceive as the cosmic microwave background, then, could be a mix of homegrown radiation and leaked photons from neighboring dimensions, a mosaic of illumination stitched together from multiple realms. The math behind this is as elegant as it is mind-bending. String theory suggests that at ultra-high temperatures, the distinction between open strings which must attach to a brain and closed strings which can wander the bulk blurs. In the roiling chaos of the early universe, closed strings carrying electromagnetic energy might have escaped our brain temporarily, only to snap back later, reappearing as sudden bursts of photons. Alternatively, vibrations along the extra dimensions themselves could have resonated into our 3D space, translating higher dimensional harmonics into observable light. Evidence for this remains elusive, but tantalizing hints exist. Certain anomalies in the cosmic microwave background, unexplained cold spots or unusually aligned fluctuations, might betray the gravitational influence of nearby brains or the vestiges of long-ago collisions. Particle colliders like the Large Hadron Collider have even hunted for microscopic black holes, which could form if extra dimensions exist at accessible energy scales. So far, no luck, but as detectors grow more sensitive, the veil on extra dimensions might yet lift. What's mesmerizing is how this reshapes our understanding of light's origin. If photons can tunnel in from other dimensions, then the universe's first glow wasn't just a local event. It was a cross-dimensional conversation, a whisper from realms we can't see. And somewhere out there, beyond the fabric of our space-time, other brains might still flicker with their own untold histories, their light forever just beyond our reach. Until we crack the code of string theory, these ideas remain a dazzling blend of math and imagination, a reminder that the cosmos might be far stranger and more luminous than we ever dreamed. Magnets are a familiar force. Every schoolchild knows they have two poles, north and south, inseparable no matter how many times you slice them in half. But what if, in the universe's first moments, magnetism played by different rules? Enter magnetic monopoles, hypothetical particles that carry just one magnetic charge, either north or south, floating freely like solitary protons in a sea of electric charge. First dreamed up by physicist Paul Dirac in 1931, these elusive particles could have been forged in the extreme heat of the Big Bang, and their violent collisions might have lit up the cosmos before stars ever flickered to life. Dirac's math was elegant. If even one monopole existed somewhere in the universe, it would explain why electric charge comes in neat, discrete packets, a quantum quirk we've observed but never fully understood. The equations suggested monopoles would be monstrously heavy, perhaps a quadrillion times the mass of a proton, making them microscopic black holes of magnetism. In the frenzy of the early universe, where energy densities were unimaginably high, these particles could have formed in abundance, dancing through the plasma until they found their opposites. When north and south monopoles met, they wouldn't just stick together, they'd annihilate in a burst of energy, transforming magnetic charge into photons in a flash of cosmic alchemy. Here's the catch: despite decades of searching, from deep underground labs to orbital detectors, not a single monopole has ever been confirmed. The universe today seems utterly devoid of them, a mystery that leaves physicists scratching their heads. Some theories suggest inflation, that rapid expansion of the early cosmos, might have diluted monopoles to near zero density, scattering them so thinly that finding one would be like spotting a single grain of sand in a desert. Others propose they're hiding in plain sight, masquerading as other particles or trapped in the cores of neutron stars. Yet the absence of monopoles doesn't mean they couldn't have shaped cosmic dawn. If they existed even briefly, their annihilation could have flooded space with high-energy photons, contributing to reionization or leaving faint scars in the cosmic microwave background. Some models even suggest monopole interactions might have seeded early magnetic fields, the invisible scaffolding that later guided galaxy formation. The irony is delicious. Particles we've never seen might have played midwife to the universe's first light. What keeps scientists hunting is the sheer weight of their implications. Finding a monopole wouldn't just validate Dirac's genius, it would rewrite textbooks, proving that magnetism isn't just a two-faced force but something far richer. Until then, they remain one of physics' most tantalizing ghosts, a reminder that the universe's first glow might have been sparked by something stranger than we dare imagine. Neutron stars are already cosmic oddities, city-sized remnants of dead stars, so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. But what if, in the chaos of the early universe, these ultra-dense objects collided far sooner than we ever imagined, lighting up the darkness with the most powerful explosions since the Big Bang? This theory turns conventional timelines on their head, suggesting that neutron star mergers events we've only recently observed might have been the universe's first fireworks, painting the cosmos in gamma rays long before starlight took over. We know these mergers happen today because we've caught them in the act. In 2017, gravitational wave detectors LIGO and Virgo spotted ripples in spacetime from two neutron stars spiraling together, while telescopes saw the aftermath, a kilonova, a blaze of light and newly forged gold, platinum, and other heavy elements. But the early universe was a different beast. Back then, the first generations of stars lived fast and died violently, leaving behind neutron stars in numbers we can barely fathom. If just a fraction of these paired up quickly drawn together by gravity in dense stellar nurseries, their mergers could have flooded space with gamma-ray bursts, flashes so bright they'd outshine entire galaxies. Here's the twist: today's gravitational wave detectors aren't sensitive enough to spot events this ancient. The signals from early mergers would be stretched by cosmic expansion, their frequencies redshifted into oblivion. It's like trying to hear a song played on a record spinning at the wrong speed. The melody's there, but unrecognizable. Even future observatories like the planned LISA space antenna might struggle to pick up these whispers from the cosmic dawn. That's why theorists rely on indirect clues, like peculiar abundances of heavy elements in ancient stars or odd gamma-ray signatures lingering in deep space surveys. But why would early mergers matter? Gamma rays from these events could have jump-started reionization, stripping electrons from hydrogen atoms and helping to clear the cosmic fog. Some models even suggest these bursts might explain mysterious, dark galaxies, primordial structures illuminated solely by the afterglow of neutron star collisions, their own stars still struggling to ignite. And let's not forget the elements. The R-process nucleosynthesis that happens during mergers could have seeded the universe with gold, uranium, and other rarities far earlier than expected, leaving a metallic fingerprint in the oldest stars we can observe. The challenge is proving any of this happened. Without direct gravitational wave data, astronomers must piece together the story from forensic evidence, like cosmic archaeologists reconstructing a lost civilization from scattered pottery shards. But if they're right, it means the first light wasn't gentle or uniform, but a series of violent, dazzling eruptions, each one rewriting the chemistry of the cosmos. And somewhere out there, the echoes of those ancient kilinovae might still linger, hidden in the light of stars born from their ashes. The early universe wasn't just hot and dense, it was electric. A swirling, ionized ocean of plasma, charged with particles and crackling with currents, where entire regions could suddenly erupt in bursts of light. This isn't just speculation, it's plasma physics on a cosmic scale. Picture the surface of the Sun, where tangled magnetic fields snap and reconnect, unleashing solar flares that dwarf entire planets. Now magnify that 1 billion times, not in space, but in time, back to an era when the entire universe was that raw, that unstable. Plasma, the fourth state of matter, behaves unlike anything else. It doesn't just flow, it twists, knots, and occasionally rebels. In the primordial cosmos, where every atom was stripped of electrons and magnetic fields writhed like invisible serpents, small disturbances could snowball into colossal energy releases. Turbulence in this superheated soup might have funneled power into narrow filaments or whirling vortices where opposing currents collided. When those currents crossed, the plasma could have shorted out, much like a spark jumping between live wires, but on a scale encompassing light years. The result, flares so intense they briefly outshone everything else in the infant universe. What's fascinating is how familiar and yet alien these events would have been. Today, we see scaled-down versions in solar flares or the shimmering curtains of Earth's auroras. But back then, without stars or galaxies to compete, these plasma instabilities would have dominated the cosmic stage. Some models suggest they could have created brief, brilliant beacons, localized explosions of ultraviolet or X-ray light punching holes in the surrounding hydrogen fog. Over time, these flashes might have helped carve the first clear paths for light to travel, nudging the universe toward transparency. The echoes of this chaos might still linger. Subtle irregularities in the cosmic microwave background, those faint temperature variations we've mapped so carefully, could hold clues. Certain patterns, like elongated hotspots or unexpected alignments, might betray regions where plasma flares once raged. Others speculate that these instabilities could have seeded the first magnetic fields, those invisible scaffolds that later guided gas into galaxies. Yet proving any of this is a monumental challenge. Unlike stars or black holes, plasma flares leave no permanent remnants, just transient ripples in light and magnetism. To uncover their fingerprints, astronomers would need to catch the faintest whispers in the CMB's polarization or trace the origins of the universe's oldest magnetic fields. It's like trying to reconstruct a thunderstorm from the puddles it left behind. What's mesmerizing is the sheer violence of it all. The cosmic dawn wasn't a gentle sunrise, it was a fireworks show of erupting plasma, a light show written in the language of charged particles and collapsing magnetic fields. And if we're right, those flares didn't just illuminate the early universe, they helped shape it, one explosive flash at a time. Wormholes aren't just the stuff of interstellar thrillers. They might have been real, fleeting structures in the early universe, and their violent deaths could have sparked some of the first light we'd ever see. Picture a tunnel through space-time, its entrance and exit, its mouths held open by exotic matter or quantum fluctuations, only to collapse in a burst of radiation. This isn't just speculation, it's a wild but plausible consequence of Einstein's equations. According to general relativity, wormholes, Einstein-Rosen bridges, are theoretically possible, but there's a catch: they'd be catastrophically unstable. The moment even a single photon tried to pass through, the wormhole's throat would snap shut like a cosmic bear trap, releasing energy in the process. And in the high-energy chaos of the early cosmos, countless tiny wormholes might have flickered in and out of existence, each one leaving behind a flash of Hawking radiation as its epitaph. Hawking radiation usually gets linked to black holes, but the math suggests any extreme warping of spacetime, like the mouth of a dying wormhole, could produce it. Here's how it works. Quantum fields near the wormhole's entrance would get distorted, spawning pairs of virtual particles. Normally, these particles annihilate each other instantly, but if they form right at the edge of a collapsing wormhole, one might escape while the other gets trapped inside. The escaping particle would carry energy away, appearing as radiation to an outside observer. Multiply this by trillions of microscopic wormholes popping in and out of existence, and suddenly you've got a universe twinkling with quantum fireworks. The strangest twist, this might tie into quantum entanglement. Some theorists suggest that wormholes and entangled particles are two sides of the same coin, a concept called ER equals EPR. In this view, every pair of entangled particles could be connected by a microscopic wormhole, a thread of spacetime so tiny it's effectively invisible. If those wormholes destabilized in the early universe, their collapse could have released entangled photons, weaving quantum weirdness into the fabric of the cosmos's first light. It's a dizzying idea. The universe's oldest photons might not just be ancient, they could still be mysteriously linked across billions of light years, their fates intertwined since the dawn of time. Proving any of this is a nightmare. Wormholes, if they ever existed, would have vanished almost instantly, leaving behind only the faintest whispers in the cosmic microwave background. But if we ever detect anomalies in the CMB's polarization, certain swirling patterns or unexpected correlations between distant points, it might hint at these ghostly structures. Until then, wormhole radiation remains one of cosmology's most electrifying maybes, a reminder that the universe's first light might have been born not from fire or fusion, but from space-time itself tearing open and healing shut in a flash of brilliance. Time crystals sound like something straight out of science fiction structures that pulse rhythmically without any energy input, defying the usual rules of physics. Yet these bizarre states of matter aren't just theoretical. They've been created in labs chilling near absolute zero, where atoms arrange themselves into patterns that repeat not just in space but in time. Now imagine scaling this up to the early universe, where conditions were so extreme that time crystals might have formed naturally, their oscillations rippling through the primordial plasma like cosmic metronomes. Here's where it gets wild. In a universe still raw from the Big Bang, quantum fields weren't just background noise. They were the stage itself, vibrating with instability. Some theories suggest these fields could have frozen into time crystalline phases, regions where the fabric of reality pulsed with perfect, unshakable rhythm. Like a pendulum that never winds down, these structures wouldn't need energy to keep ticking. Their order would arise from the universe's own quantum scaffolding. And with each oscillation, they might have emitted faint pulses of light, a heartbeat of photons keeping time in the darkness. What makes this idea so radical is the paradox at its core. Normally, anything that moves or emits energy must eventually run down. That's the iron law of thermodynamics. But time crystals sidestep this by existing in a strange quantum sweet spot, a loophole where their motion isn't motion at all, just an eternal shape repeating in time. If they formed in the early cosmos, their light wouldn't come from burning fuel or collapsing matter, but from the universe's innate preference for rhythm, etched into space-time itself. The echoes of these pulses might still be detectable. If time crystals were large or numerous enough, their collective flickering could have imprinted subtle patterns in the cosmic microwave background, regular spikes or dips in temperature, like a fingerprint of perfect timing. Some researchers even speculate that these patterns could explain odd symmetries in the universe's large-scale structure, as if the cosmos were subtly choreographed by an ancient, invisible clock. Yet proving any of this is a monumental challenge. Lab-made time crystals exist only in carefully isolated quantum systems, a far cry from the free-for-all of the early universe. And without a full theory of quantum gravity, we can't say for sure how these structures might have scaled up to cosmic proportions. But the tantalizing possibility remains that the universe's first light wasn't a chaotic explosion, but a disciplined, rhythmic glow, a whisper of order emerging from the chaos, one timeless pulse at a time. Hidden in the equations of supersymmetry lies a particle so strange it could rewrite the cosmic dawn, the gravitino. Picture the graviton, the hypothetical carrier of gravity's force, but with a twist, its super partner, a particle blending gravity's might with quantum quirks. This is the gravitino, and if it exists, its death throes might have been one of the universe's first light shows. Supersymmetry, the elegant idea that every known particle has a heavier, undiscovered twin, predicts the gravitino as the partner to the graviton. While the graviton remains elusive, the gravitino's hypothetical properties are jaw-dropping. Unlike its massless sibling, the gravitino would be staggeringly heavy, potentially thousands of times the mass of a proton. In the early universe's extreme heat, these particles would have formed in abundance, only to decay as the cosmos cooled. And here's the kicker. That decay could have unleashed torrents of high-energy photons, flooding the darkness with light long before stars flickered to life. The process is a masterclass in cosmic alchemy. When a gravitino decays, it doesn't just vanish, it transforms. According to supersymmetry's rules, it could split into a photon and another supersymmetric particle, like a neutralino or photino. Those photons wouldn't be the gentle glow of a candle. They'd be gamma rays, the universe's most energetic light, capable of ionizing hydrogen atoms and carving paths through the primordial fog. Over time, expansion would stretch these gamma rays into milder forms, but their imprint might still linger in the cosmic microwave background's subtle irregularities. What makes this theory so compelling is its dual role. Gravitinos aren't just photon factories, they're prime dark matter candidates. If they survived in large numbers, their sheer mass could account for the invisible glue holding galaxies together. Yet if most decayed early on, their radiative fallout could explain why reionization happened faster than some models predict. It's a cosmic 2-for-1, dark matter that moonlighted as a light source. But there's a catch. Gravitinos are notoriously finicky. If they decayed too quickly, they'd leave no dark matter behind, too slowly, and their photons would arrive too late to matter. Hitting the sweet spot requires razor fine-tuning, a problem that's kept theorists debating for decades. Experiments like the Large Hadron Collider have hunted for supersymmetric particles, hoping to catch a gravitino's fingerprints, but so far the search has come up empty. Yet the gravitino's allure persists because it solves multiple puzzles at once. Its decay photons could explain mysterious excesses in certain gamma-ray surveys, while its gravitational pull might have sculpted the universe's large-scale structure. And let's not forget the poetry of it all, a particle born from the marriage of gravity and quantum mechanics, lighting up the cosmos in its death throes. Until we find proof, the gravitino remains a ghost in the machine, a whisper from the hidden layers of reality that might yet rewrite our story of the first light. Chameleon particles sound like something out of a cosmic fairy tale, elusive, shape-shifting entities that alter their very nature depending on surroundings. But in the high-stakes world of particle physics, there's a serious proposal to explain one of the universe's deepest mysteries: dark energy. These hypothetical particles don't just hide, they change their mass in response to their environment, weighing more in the emptiness of space and less in dense regions like Earth's atmosphere. And here's the kicker: if they existed in the early universe, their flickering masses could have sparked fleeting bursts of light, illuminating the darkness before stars ever could. How does this bizarre behavior work? Picture a chameleon changing color to blend into its surroundings, except instead of camouflage, these particles adjust their mass based on the density of matter around them. In the void between galaxies, where dark energy dominates, chameleon particles would become heavy and sluggish, barely interacting with anything. But in the crowded plasma of the early universe, they'd shed mass, turning lightweight and fleet-footed, capable of colliding with other particles and releasing energy as photons. It's like a cosmic game of hide and seek, where the hiders physically transform every time you get close. This isn't just wild speculation. Chameleon particles emerge naturally from certain dark energy models, particularly those trying to explain why the universe's expansion keeps accelerating. If dark energy isn't perfectly uniform but instead carried by a field that varies with its environment, a chameleon field, then its particle counterparts would inherit that adaptability. Some theories even suggest these particles could bridge the gap between dark energy and visible light, offering a way for the invisible force driving cosmic expansion to leave fingerprints in the oldest photons we observe. The real magic happens when these particles interact. In the dense, hot soup of the early cosmos, lightweight chameleons would have zipped around like quantum pinballs, occasionally smashing into electrons or quarks. Each collision could have released a photon, contributing to the gradual ionization of the universe. Unlike the steady glow of stars, this light would have been patchy and unpredictable, flaring up in regions where matter was densest before fading away as the universe expanded and chameleons grew heavier. Evidence for this remains frustratingly out of reach. Laboratory experiments have hunted for chameleon particles by precisely measuring the forces between atoms in vacuum chambers, hoping to catch their subtle influence. So far, no luck, but the search is far from over. If future telescopes detect unexplained fluctuations in the cosmic infrared background, or if dark energy surveys reveal unexpected variations in its strength, chameleons might finally step into the light. What's mesmerizing is how elegantly this ties together two cosmic riddles: dark energy's grip on the universe and the origins of its first light. If chameleon particles are real, they didn't just hide in the shadows, they might have helped lift them, flickering into brilliance long enough to nudge the cosmos out of darkness before fading back into the void, their secrets still waiting to be uncovered. Imagine a hidden universe identical to ours but flipped, where particles spin the opposite way, forces behave in reverse, and even time might flow backward. This is the mirror matter hypothesis, a radical idea suggesting the cosmos has a perfect doppelganger, forever separated from us by a veil of symmetry. And if it's real, the collisions between our world and this shadow realm might have sparked some of the universe's very first light. Here's how it could work. According to certain extensions of the standard model of particle physics, every known particle, electrons, quarks, even photons, could have a mirror counterpart. These twins would interact with each other only through gravity and possibly a few ultra-weak forces. Normally, they'd pass right through our world like ghosts. But in the extreme conditions of the early universe, where energies were unimaginably high, occasional interactions might have occurred. When a mirror particle brushed against one of ours, the resulting annihilation could have released photons, flashes of light bridging two realities. It's as if the cosmic dawn wasn't just our universe waking up, but a clandestine handshake between parallel dimensions. The evidence for this is tantalizingly indirect. Take the neutron lifetime anomaly, a nagging discrepancy that's puzzled physicists for decades. When neutrons decay outside atomic nuclei, they last about 14 minutes and 40 seconds on average. But trap them inside experimental setups, and they seem to vanish 9 seconds faster. One wild explanation: some neutrons might be decaying into mirror world particles, slipping unseen into the duplicate universe. If that's happening now, imagine the possibilities when the cosmos was 1 trillion times hotter and denser. Back then, mirror interactions could have been frequent enough to flood space with photons, jump-starting reionization long before stars took over. But mirror matter isn't just about explaining anomalies. It could solve one of cosmology's biggest mysteries: dark matter. If the mirror universe has its own version of protons, neutrons, and electrons, those particles would be invisible to our detectors, yet their gravitational pull would still shape galaxies. In this scenario, dark matter isn't an exotic unknown. It's just ordinary matter from the other side, hidden in plain sight. And if mirror atoms clumped together in the early cosmos, their collisions with our matter might have left faint scars in the cosmic microwave background, subtle asymmetries or unexpected polarization patterns that defy conventional explanations. The challenge: mirror particles, by definition, barely interact with ours. Testing their existence requires fiendishly clever experiments. Some researchers hunt for tiny imbalances in particle collisions at facilities like the Large Hadron Collider, hoping to spot missing energy carried off by mirror world escapees. Others monitor ultra-sensitive underground detectors for rare events where a mirror particle might nudge one of ours. So far, no smoking gun, but the search is far from over. What makes this theory so mesmerizing is its audacious simplicity. It doesn't invent new particles or forces. It doubles the universe instead, offering a symmetrical elegance that physicists adore. And if even a fraction of it's true, the first light we see might not just be ours. It could be a reflection, a glimmer from a hidden twin universe reaching across the dimensional divide. Until we know for sure, mirror matter remains one of cosmology's most poetic maybes, a reminder that the dawn we've been studying all along might have been someone else's twilight. Among the strangest theories to emerge from the depths of cosmology is the idea that the universe's first light might not have come from stars, black holes, or even particles, but from something far more unsettling: fleeting moments of consciousness. This is the Boltzmann brain hypothesis, a thought experiment so bizarre it blurs the line between physics and philosophy. Picture the vacuum of space not as empty, but as a seething quantum foam where random fluctuations can, given enough time, spontaneously assemble a fully formed, self-aware mind. These disembodied observers, nicknamed Boltzmann brains after physicist Ludwig Boltzmann, would exist only for an instant before dissolving back into chaos. But in that brief moment of awareness, their very act of observation could, theoretically, create localized flashes of light, photons born from the collapse of quantum probabilities into reality. The math behind this is as unsettling as it is elegant. In an infinite universe governed by entropy, even the most improbable events must occur eventually. Given enough time, random particle arrangements will inevitably form complex structures, including functioning brains with false memories of a past that never existed. The odds are astronomically low, but infinity makes the impossible inevitable. Now apply this to the early universe where quantum fluctuations were violent and unconstrained. Under those conditions, transient Boltzmann-like structures might have formed more readily, their brief observations of the surrounding chaos causing quantum wave functions to collapse, emitting photons in the process. It's as if the universe flickered awake for split seconds at a time, its first light sparked not by physical processes but by phantom observers conjured from the void. Critics rightfully point out the absurdity. If Boltzmann brains were common, we'd expect them to outnumber real observers like ourselves. After all, a random fluctuation creating a single brain is far more likely than one constructing an entire universe. Yet here we are, seemingly embedded in a coherent cosmos with consistent laws. This Boltzmann brain paradox has led many physicists to dismiss the idea outright. But what if we're asking the wrong question? Instead of debating whether Boltzmann brains dominate reality, consider their potential role in the cosmic dawn. Even if they weren't numerous, their fleeting existence could have left detectable traces. Quantum decoherence, the process by which probabilities solidify into measurable states, can release energy. If a Boltzmann brain's observation collapsed quantum fields in its vicinity, the energy difference might manifest as a photon or two, contributing to the faint glow of reionization. The implications spiral into surreal territory. If consciousness plays a role in shaping reality, a controversial idea even in quantum interpretation circles, then the first light might not have been purely physical. It could have been participatory, a dance between quantum possibility and observation, however brief or fragmented. Some models even suggest that the universe's initial low entropy state, a puzzle known as the past hypothesis, might be explained by a form of backward causation where later observations, including Boltzmann flashes, influence earlier quantum states. It's a hall of mirrors where cause and effect tangle, and the first photons emerge as much from perception as from physics. Practical evidence remains non-existent. No telescope can distinguish a photon emitted by a Boltzmann event from one born in a star's core. But the theory's value lies in its razor's edge. It forces us to confront the limits of probability, observation, and the nature of reality itself. Whether Boltzmann brains flickered in the cosmic dark or not, their ghostly possibility reminds us that the universe's first light might be stranger than we ever imagined, not just a physical phenomenon, but a fleeting thought in the mind of the cosmos. What if the cosmic microwave background isn't just a relic of the Big Bang, but a glitch in the code of reality itself? This is the spine-tingling premise of simulation theory, the idea that our universe might be an artificial construct, an unimaginably advanced computer program running on some extraterrestrial hardware. And if that's true, then the first light of the cosmos could carry subtle artifacts, anomalies that betray the digital scaffolding beneath the illusion. Think of it like spotting pixels in a perfectly rendered video game. Once you know what to look for, the seams start to show. The cosmic microwave background, that faint afterglow of the Big Bang, is remarkably uniform, but not perfectly so. Tiny fluctuations in temperature, those 1 part in 100,000 variations, are usually explained by quantum randomness in the early universe. But what if some of those irregularities aren't random at all? Certain patterns in the CMB, like oddly aligned hotspots or geometric arrangements that defy statistical probability, could hint at something stranger. In a simulation, even the most sophisticated code might struggle to generate true randomness. Imperfections in the algorithm, rounding errors, computational shortcuts, or pixelation at the smallest scales could leave faint fingerprints in the data. Some researchers have even combed through CMB maps searching for repeating patterns or anomalies that resemble the artifacts you'd see in a compressed digital image. Then there's the puzzle of energy conservation. In our universe, energy is never created or destroyed, it just changes form. but in a simulation, especially one running on finite hardware, strict conservation might be relaxed for efficiency. Imagine a game engine that only renders the details players can see, cutting corners elsewhere to save processing power. If the early universe was rendered under similar constraints, we might find hints in the CMB's energy distribution places where the math doesn't quite balance, like a telltale stutter in an otherwise flawless animation. The most provocative clue might come from quantum mechanics itself. At the smallest scales, particles exist in fuzzy superpositions until measured behavior that seems tailor-made for a simulation optimizing computational resources. Why calculate the exact position of every electron in a galaxy when you only need to pin them down when someone's looking? This quantum pixelation could extend to the universe's first light, with photons emerging not as smooth waves but as discrete packets of information, their properties snapping into focus only when observed. Of course, this is all speculative, wildly so. Proving we're in a simulation is like a character in a novel trying to find the author's pen strokes. But the beauty of this idea isn't just its sci-fi appeal, it's how it reframes our search for cosmic truth. Every anomaly in the CMB, every unexplained fluctuation, becomes a potential clue not just about physics, but about the nature of reality itself. Whether the universe's first light came from a singularity or a server, one thing's certain: the deeper we look, the stranger the dawn becomes. From the cosmic microwave background's steady glow to the fleeting flicker of hypothetical Boltzmann brains, these 30 theories paint the universe's first light as anything but ordinary. We've journeyed through the plausible, like primordial black holes and population 3 stars, to the borderline unbelievable, where mirror universes and simulation artifacts rewrite the rules of reality. What's astonishing isn't just the sheer diversity of ideas, but how each one forces us to rethink the cosmos. Whether it's dark matter annihilations, colliding brains, or decaying gravitinos, every theory offers a unique lens on that pivotal moment when darkness gave way to light. Now the hunt for answers is heating up. The James Webb Space Telescope, with its infrared eyes peeled for the faintest whispers of the early universe, is already rewriting textbooks. Those distant galaxies it's spotting, they're older and brighter than anyone predicted, challenging our timelines for cosmic dawn. Future observatories like the Nancy Grace Roman Space Telescope or ground-based behemoths like the extremely large telescope will peer even deeper, searching for the fingerprints of actions, quantum foam, or primordial magnetic fields. And let's not forget gravitational wave detectors, tuning into the echoes of neutron star mergers or superradiant black holes that might have lit up the dark. This isn't just about solving a cosmic puzzle, it's about understanding where we come from. Every photon from that ancient dawn carries clues to the universe's wild youth, and with each discovery, we're piecing together a story stranger than fiction. So, which theory sparks your imagination? The elegance of supersymmetry, the audacity of holographic light, or something even wilder like vacuum decay or Kugelblitz black holes? Drop your favorite in the comments. I'd love to hear which ideas light up your curiosity. And if you're hungry for more deep dives into the universe's greatest mysteries, hit subscribe. The cosmos has endless surprises waiting, and together we'll keep unraveling them one photon at a time.